Hello, in this video, we're going to talk about the central limit theorem and its applications. You can follow along using your 6.4 central limit theorem guided notes. And it also goes along with section 6.4 in your textbook. So the central limit theorem, it tells us that for a population with any distribution, the distribution of sample means approaches a normal distribution as the size increases. So think about section 6.3 where we were exploring this idea with taking the mean of sample means and seeing how they compared to our population mean. We have a procedure in this section that forms the foundation for estimating population parameters and for hypothesis testing, which is our next unit. Given the original population has a mean, mu, and a standard deviation, sigma, and also given a simple random samples of the same size n are selected from the population, we can make the following conclusions. The distribution of the sample means x bar will, as the sample size increases, approach a normal distribution. The mean of the sample means is the population mean, because remember, the mean of the sample means targets the population mean as you do more and more samples. The standard deviation of the sample mean doesn't target, but what we say is that it's the sigma over the square root of n. Let's look at some rules for how we would actually apply this. Practical rules for real applications involving a sample mean, x bar. For sample means of size n is larger than 30, the distribution of the sample means can be approximated reasonably well using a normal distribution. So if we have n greater than 30. The approximation becomes closer to a normal distribution as the sample size n becomes larger. But if we already know that our population is normally distributed, as it says in the second rule here, then for any sample size n, the sample means will be normally distributed, not just for values greater than 30. So our first rule, if n is greater than 30, we didn't need to know whether we had a normal distribution. But if we already know we have a normal distribution, it's okay if we have a smaller sample size. There's some notation that we'll see. The mean of the sample means will be mu of x bar. That subscript means that it's the mean of the sample means. And that is equal to the population mean. Remember, because the mean of the sample means targets the population mean. The standard deviation of the sample means is sigma sub x bar will be the standard deviation of x divided by the square root of n. It's also called the standard of error. So we're dividing by that square root of n to correct for error. So as the sample size increases, remember the sampling distribution of sample means is going to approach a normal distribution. And we talked about that in detail in our last section. Now we're going to look at two very similar examples that involve IQ scores. And these examples will demonstrate the importance and the difference of when we're using the central limit theorem and when we're not. So here we go. Given that we have for normal IQs, the mean is 100 and the standard deviation of the population is 15, we want to find the probability that a single IQ is greater than 115. We're not using the central limit theorem here, and it's because we're just finding the probability for a single IQ score being greater than 115. So we're finding P of IQ greater than 115. But because it's a single IQ score, we're just going to do what we did in sections 6.1 and 6.2 with normal distributions. So our first step is to label a diagram. The mean is 100. I know the standard deviation is 15, and we're finding the probability of IQ is greater than 115. So I'll label 115, and I'll shade the area that comes after it. And I know my X score, and I'm trying to find my probability, P. So I'm going to use my calculator to do that. So the probability that the IQ is greater than 115, I'll use normal CDF, because that's what I use when I have my numbers, my bounds, but I'm trying to find a probability. And my lower bound will be 115. My upper bound will be just some large number that's at least 4 standard deviations out. Mean is 100, standard deviation is 15. Our calculator, we have second vars. Normal CDF is option 2. And we'll type in 115. For our lower limit, upper limit, I'm just going to put 9999. Our mean is 100. And our standard deviation is 15. And then go ahead and calculate. You should get 0.159. During your work, you have not just the answer, but you want to have this required statement of what you put in your calculator. For part B, we're finding the probability of 36 people with a mean IQ of greater than 115. We use the central limit theorem here because we're finding the probability that the mean is greater than 115. When you're finding the probability for a mean being greater than or less than some number, that's your cue to be using the central limit theorem. And we have here 36 people. That is greater than 30, so we can assume a normal distribution. That's great because we can do this problem using our normal CDF. So I'm going to draw my diagram, and we still have the same mean here of our sample means, mu sub x bar, is going to be 100. And we're still trying to find a value greater than 115. So it's the same shading. Now we need to identify our point estimate, right, for the mean of the means here. We have still is going to be 100. So the mean doesn't change in this problem, but we're going to take our standard deviation, which was 15, and we're going to divide it by the square root of n. So that would be the square root of 36. Or 15 divided by just 6, giving us 2.5. So let's go ahead and make our calculations. So I'm going to use normal CDF. My lower bound is 115 on my diagram. My upper bound has to be at least 4 standard deviations out, but I'm just going to use 9999. It's easy to type in. The mean is the same, 100. And the only thing that changes in a problem using central limit theorem is that your standard deviation is going to be this number we calculated here. And when you're putting it into your calculator, you can go ahead and just type in 15 divided by the square root of 36, because we come up with a nice number in this one, 2.5, but sometimes we'll have something rounded and we want to avoid rounding in the middle of a calculation. So you can always just type 15 division sign square root of 36 right into the appropriate section on your calculator. So now we're going to go second and press vars because that's where distribution stuff is. Press the number 2 for normal CDF. Our lower limit's 115, our upper limit's the same, our mean is the same, but now instead of just 15, we're going to do 15 divided by the square root of 36. You could have put in 2.5, that would be okay. I just want to demonstrate to you that you can actually put in the calculation and you'll still come up with an answer. And we get 9.9 e negative 10. I get 9.9 e negative 10. If you wrote this on your paper, I wouldn't give you full credit. What that means is 9.9 times 10 to the negative 10. And that rounds to 0, but we know it's a little greater than 0, so we'll put 0 plus. Note that the probability of a single person with an IQ score of greater than 115 is much more likely than having the mean of 36 people's IQ scores be greater than 115. Next, suppose an elevator has maximum capacity of 16 passengers and a total weight of 2,500 pounds. Assuming a worst case scenario in which all the passengers are male, that's only worst case because on average males have a higher body weight. What are the chances that the elevator is overloaded? And we want to assume the weights follow a normal distribution with a mean of 182.9 and a standard deviation of 40.8. So first we want to find the probability that one randomly selected male has a weight that's greater than 156.25. And that 156.25 is gotten by taking 2,500 and dividing it by 16. So what we need to do first is draw a diagram. The mean's 182.9, and we're looking for a weight higher than 156.25. So from here, we can use normal CDF. Our minimum is where our shading begins, is 156.25. Our maximum, we can just use some high number. The mean is 182.9, and the standard deviation is 40.8. Go ahead and put that in your calculator. Come up with 0.743 for your probability that one male is greater than 156.25 pounds. For part B, we're finding the probability that a sample of 16 males have a mean weight greater than 156.25 pounds. Because we're talking about a mean here, we're going to be using the central limit theorem, CLT for short. So, similar problem once again. We'll draw our diagram. We have our center at 182.9. Only this time it's representing the mean of the means, right? We have 156.25, and we're shading to the left. So we're going to use normal CDF of 156.25, high number 9999 for our upper bound. The mean stays the same at 182.9, but it's our standard deviation that's going to change. The standard deviation won't be just 40.8, it'll be 40.8 divided by the square root of 16. You can put that right in your calculator in that format, or you can calculate the actual number first. And you'll get 0.996. So the probability that the mean weight of the 16 males is greater than 156.25 pounds is 0.996. It's almost certain. Now, we've practiced a number of examples together. It's your job now to complete examples 3 and 4.